now I'm already recording now.
It's recording. Okay, great. Thank you.
I'm recording now.
Okay, thank you. So you can keep.
So now you have. I hope you still see my screen.
Yes, I saw. I see.
Okay, so now you need to insert 1, 2, 3, 4, 5, 6 values. You need to insert 6 values for 4 entries. Okay, for 4 entries into the financial advisor table. So how can we solve this? Just give me a second. I will show you what I mean. Like you can see, and also brand, you can also compare with what you have done.
Yes, yes, I can. Maybe the sharing of my screen would help you to explain. I just share my screen. Just a second.
Okay, you can show your screen. Yes.
Okay, can you see it? It's Heidi SQL,
Just
and this is
yes. Now I can see. Now I can see.
yeah. Okay, this is the database, and for the first question, I wrote this little SQL, this one. Yes. So
Could you just please zoom in a little bit?
I'll try. Let's have a look. How can we?
I put the answer in chat, Torla. So
Shall I copy
I am reading.
no. I just need from you to compare the one I put in chat with your solution, and explain to us how did you solve it.
Okay.
But you don't write any relationship.
No, it's the idea here. The idea here from this task, if you read the requirement here, it's saying write SQL statements used to insert the
Okay.
data shown in the above image. So you wanted from this task, or you are asked to enter these values using insert statement. This is the task, to
Okay, then I
insert.
didn't understand. Okay.
Okay, could you explain, Brand, what you did?
Yes, yes. I just took a copy from the last session in this session number 5. So in my first row, I deleted from this copy every rows, and then I insert into exercise 5 financial advisor clean, and this is the declaration of the columns, and this is the declaration of the values. 4 rows.
Is it clear for you? Is it clear for you, Torlak, now? Somehow?
Yes.
Okay, the second one, modify the financial advisor ID field so that its value automatically increases for each new inserted record. So you wanted to make something called what? Like to make this automation. Do you remember? Brand, did you think about the
Yes,
second one?
yes, I have opened the SQL statement here right now. It's an order table, financial advisor clean, and it's modify financial advisor ID. And the Mariah DB manual said I have to declare it complete. This column I have to declare complete. So I declared again integer 11 and
Yeah.
then auto increment.
Exactly. Just this word, auto increment. Auto increment. It means this field, you don't need to enter the value. It will be automatically increased by one. So this is every time when you insert a new entry, it will be automatically assigned a new number. Integer. It means int. It means integer value. So every time it will be increased when you enter a new values into the rows. Is it clear for you, Turlak, as well? This one now?
Yes, now I understand. But sometimes I try to play with this on the SQL. It can see it can be like 600 time auto increment. That means 600 time I insert this or I use it.
No, no, you just write once, but
Hmm.
this will be applied to the whole column.
Oh, okay.
So now we do alter table. It means we now are adjusting or changing the schema of the table. Okay, the number three, Brent.
Yeah, just loaded. The number 3 is insert Susan. Okay, it looks like this. It's insert into.
Yeah.
This is the name of the database. And again, the declaration of all the columns.
Yeah.
And the values. But now, in difference to the number 2, we declared the value for the ID. And now we did auto increment. And now we do not have to declare the value for the ID.
Exactly.
It will be added. I can let it run so we can have a look. Let's have a look. Now it looks like this. And
Yeah.
now we let the insert run.
Yeah.
Doesn't have the default value. Okay.
What did you change?
A default value. He wants a default value. Oh, that's interesting. Okay, I will something. I'll do the. I have 2 copies. I will.
You can check the one I added in chat. I added in
Now,
chat the solution.
now it works. Now it works. Now it works. I had just to alter the name of the database. And if we look now, this is the old version, and this is the new version, and this is number 6, Susan. This is the table.
Number 4.
Yeah.
Number 4.
It's number 6 is Susan.
Mm.
We had to delete all the rows where branch ID is 1. Unfortunately, I did this before. So 1, 2, and 5 are missing because all these 3 had branch ID number 1. But what is interesting, although they were deleted, the database remembers that the next ID is 6. Although 5 is deleted and 1 and 2 is deleted.
I see.
That's interesting for me too. I imagine that he would go on with 5, but that's not true. Somewhere in the background, he knows that there were originally 5 rows, and now he takes number 6. Very intelligent.
Okay, for number 4, I added the solution here. You need just to update the phone number of Susan. So you just update the table name, financial advisor. You set the financial advisor phone number, and you put equal the new value. Okay,
Okay.
where this is the
Okay.
condition. Financial advisor ID equal 5. So this is this is the condition to update, for update. And number 5, add a constraint to ensure that the phone number can't be empty. So now we need to change the schema. Number 5, so alter table financial advisor, modify financial phone number varchar 45 not null. So in the future you can't leave any entry null for this column. Number 6, you what you need in this task to delete all the financial advisors working at branch 1. So in that case you need to delete from your, as in chat here, delete from financial advisor where branch ID equal 1. So you will delete all the financial advisors who have branch ID as foreign key equal 1. So I think it's more clear for you now, Turluk.
Yes.
Okay, so let's start our new lecture. It's really very interesting because it's talking about not only SQL and
May I
and
may I
this.
just interrupt for a second? There
Yeah,
were two more questions in the transfer task, and with the last one, I have a problem I cannot solve.
yeah. Could you share with us?
Yes, I just opened the script, the SQL script.
Yeah.
We had to drop a column branch ID. Now that's a foreign key. And when I want to do this, he says, he does. Why does he do it now? Yes, in this case, can't drop. No, that's my mistake. Sorry, no. Now I know why it doesn't work. It's okay.
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 Okay. So I also,
I
anyway, I will
stop
put
sharing. I
I'll
stop
put the
sharing.
solution here
Yeah,
in chat, like just for your
yeah,
information.
yeah.
Okay, so we
I
can start now
I
our
stop
new
sharing.
lecture. Okay.
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 Thank you.
You're welcome. Okay, so let's start our new lecture now. I'm sharing, and now I hope you can see something now.
Yes, wonderful green.
Yeah. Okay, so let's get started with this really very interesting topic. This unit 7, not only SQL database systems. So the study goals from today to understand the meaning and the need for not only SQL, discuss the difference between constraint of relation and the non-relational data models, explain the difference among different available not only SQL system types. So what we really need to understand today is the drawbacks of the relational model. Like we discussed everything about relational model or relational databases and why they are important and why we need to do this for our businesses and so on. But we need to also to understand what kind of solutions that not only that relational database can't solve, can't cover these issues. So one of them, like the relational model, is not scalable. It's not scalable. It means you define the schema, you define the design of your database from the really beginning, but when you need to extend or to make it scalable for any kind of request, like if you put that the input for this column varchar 50, so scalability means if I also need to scale the business, it means it should not be like a constraint or be based on constraints there. The structure of the relational model is complex. To make this structure of the database or relational model is complex, and you have to take care in your design about everything from the beginning. The schema definition is rigid. It means like it's based on the schema. So everything based on your design from the beginning. You said this column is a primary key. So this solution is based that you have primary key in this table called this or that and so on. So you are based on the schema. What are the two modern data management needs that lead to the adoption, if not only SQL paradigm? Why or what are the two modern data management needs? So it's the big data, like we got like applications, we big data like millions of records, a lot of records for the business, and huge amounts of data and very big numbers of users that lead us to think about not only SQL paradigms. Many in not only SQL systems are open source. What does open source mean? Does you know? Does anyone of you know what does open source mean?
The source code is laid open. Everyone can read the source code or can even work on it. And yes, that's open source.
Yeah, so open source, it means like that you can have access to the source code. So it means you can also you can when you have access, you can also modify and change, and you can build your own things based on that. So open source means is that the user also has access to the source code and can modify it. This is like the main description. Why NoSQL, or why not only SQL? So it means not only SQL is a tool. We used it like to release much of the SQL constraints, gives us like freedom, hundreds of the thousands of users, like if you have like really big data, huge amounts of data, flexibility, schema free, we don't have schema, or weak schema restrictions, high availability, scalability. These are the advantages on when we apply not only SQL into our solutions.
Big data and the NoSQL approach. It's well known that humanity today is generating data at an unprecedented rate throughout its entire history. Processing this data promptly and correctly needs more advanced tools and approaches than relational databases. The term big data has been used since the 1990s, even though at that time no one was expecting that lives in a few decades will be almost entirely dependent on data, and no one expected that humanity will be generating and communicating data at the rate we see today. Big data does not only reflect enormous amounts of data, but in addition to the volume, the term characterizes the variety of data, which is, unlike in relational databases, under the concept of big data, It could be semi-structured or unstructured. Big data is also characterized by its velocity, which means that it is generated in series very quickly, and the values in these series change also very quickly. The veracity and value of the big data describe the truthfulness of the data and to which extent this data is worthy. These vast amounts of data generated on Earth daily and its variety cannot be all processed using only one model, which is the relational model, at least not efficiently. This is why other models are used, one of which is the NoSQL model, sometimes known as not only SQL. One of the main characteristics of NoSQL is that it does not require a definition of a schema or a structure. There are no tables, no relations, and it's much more flexible concerning the constraints enforced by the relational model. The other important characteristic is distributivity. It won't be possible to store these amounts of data on one machine or server, and thus they need to be held on several servers. There are several types of NoSQL databases, namely the key value stores that are mainly searchable by a key value, the document stores that store the records using XML or JSON. There are also graph databases, among other types of NoSQL databases.
So the properties for NoSQL, the underlying the data model is not relational, distributed and horizontal scalability, growing data, increasing users, simple replications, it's possible, semi and unstructured data. It can cover this. Relational database. Relational database can't solve this issue with semi and unstructured data. Unstructured data, it's kind of like you are expecting like streaming data coming from sensors, from hardware, from IoT devices, from videos. So you are getting different data from different sources, not in the same structured way. Structured data means you have one source of the data, you have data type, you have a specific expected data type, and you have kind of structured data, and you can organize it. But unstructured, it means you can expect different types, different values about the same data.
NoSQL databases have become very popular. Big companies rely on them to store hundreds of petabytes of data and run millions of queries per second. But what is a NoSQL database? How does it work, and why does it scale so much better than traditional relational databases? Let's start by quickly explaining the problem with relational databases like MySQL, MariaDB, SQL Server, and alike. These are built to store relational data as efficiently as possible. You can have a table for customers, orders, and products, linking them together logically. Customers place orders, and orders contain products. This tight organization is great for managing your data, but it comes at a cost. Relational databases have a hard time scaling. They have to maintain these relationships, and that's an intensive process, requiring a lot of memory and compute power. So for a while, you can keep upgrading your database server, but at some point, it won't be able to handle the load. In technical terms, we say that relational databases can scale vertically, but not horizontally, whereas NoSQL databases can scale both vertically and horizontally. You can compare this to a building. Vertical scaling means adding more floors to an existing building, while horizontal scaling means adding more buildings. You intuitively understand that vertical scaling is only possible to a certain extent, while horizontal scaling is much more powerful. Now, why do NoSQL databases scale so well? First of all, they do away with these costly relationships. In NoSQL, every item in the database stands on its own. This simple modification means that they are essentially key value stores. Each item in the database only has two fields, a unique key and a value. For instance, when you want to store product information, you can use the product's barcode as the key and the product name as the value. This seems restrictive, but the value can be something like a JSON document containing more data, like the price and description. This simpler design is why NoSQL databases scale better. If a single database server is not enough to store all your data or handle all the queries, you can split the workload across two or more servers. Each server will then be responsible for only a part of your database. To give an example, Apple runs a NoSQL database that consists out of 75,000 servers. In NoSQL terms, these parts of your database are called partitions, and it brings up a question. If your database is split across potentially thousands of partitions, how do you know where an item is stored? That's where the primary key comes in. Remember, NoSQL databases are key value stores, and the key determines on what partition an item will be stored. Behind the scenes, NoSQL databases use a hash function to convert each item's primary key into a number that falls into a fixed range, say between 0 and 100. This hash value and the range is then used to determine where to store an item. If your database is small enough or doesn't get many requests, you can put everything on a single server. This one will then be responsible for the entire range. If that server becomes overloaded, you can add a secondary server, which means that the range will be split in half. Server 1 will be responsible for all items with a hash between 0 and 50, while server 2 will store everything between 50 and 100. Theoretically, you've now doubled your database capacity, both in terms of storage and in the number of queries you can execute. This range is also called a key space. It's a simple system that solves two problems: where to store new items and where to find existing ones. All you have to do is calculate the hash of an item's key and keep track of which server is responsible for which part of the key space. Now, in this example, the range of 0 to 100 is a bit small. It would only allow you to split up your database into 100 pieces at most. So, real NoSQL databases have much bigger key spaces, allowing them to scale almost without any restrictions. Besides great scalability, NoSQL is schemaless, which means that items in the database don't need to have the same structure. Each one can be completely different. In a relational database, you have to define your table structure, and then each item must conform to it. Changing this structure isn't straightforward and could even lead to data loss. Not having a schema can be a big advantage if your application and data structure is constantly evolving. Now, at this point, it's clear that NoSQL databases have certain advantages over relational ones, but that's not to say that relational databases are obsolete. Far from it. NoSQL is more limited in the way you can retrieve your data, only allowing you to retrieve items by their primary key. Finding orders by ID is no problem, but finding all orders above a certain amount would be very inefficient. Relational databases, on the other hand, have no trouble with this. Now, there are workarounds for this issue, but only if you know how you're going to access your data, and that might not always be the case. Another downside is that NoSQL databases are eventually consistent. When you write a new item to the database and try to read it back straight away, it might not be returned. As I've explained, NoSQL splits your database into partitions, but each partition is mirrored across multiple servers. That way, a server can go down without much impact. When you write a new item to the database, one of these mirrors will store the new item and then copy it to the others in the background. This process might take a little bit of time, so when you read that item back, the NoSQL database might try to read it from a mirror that doesn't have it yet. Now, this is not a big issue in practice because data is replicated in just a few milliseconds. And if you want consistency, most NoSQL databases do have that option. So in summary, both NoSQL and relational databases will be around for the foreseeable future, each with their own strengths and weaknesses. So now you know how NoSQL works. Let's look at a few examples. Cloud providers heavily promote NoSQL because they can scale it more easily. AWS has DynamoDB, Google Cloud has Bigtable, and Azure has Cosmos DB. And to give you another example of their scalability, during Amazon Prime Day in 2019, Amazon's NoSQL database peaked at 45 million requests per second. That's mind-boggling. But you can also run NoSQL databases yourself with software like Cassandra, Scylla, CouchDB, MongoDB, and much more. Now, before ending this video, let's quickly talk about the name NoSQL. It's a bit confusing as it can have two meanings. First up, NoSQL can mean not only SQL, pointing to the fact that some NoSQL databases partially understand the SQL query language on top of their own query capabilities. And secondly, it's often called NoSQL in the sense of non-relational, because it can't easily store relational data. So that was it for this video. Please subscribe if you learned something from it, and I hope to see you.
So also, something also important about this, the relational model and the non-relational model. For usually we have atomicity, consistency, isolation, durability. This is called acid. And for the base non-relational model, it's basically availability is very high. Soft state, you can add whatever you want. Eventual consistency, it means it's based on whatever you add, it will accept it. Any type of data.
That means eventual. Could you
Still not finished. In this video, we'll continue with this explanation.
In a series of videos that will introduce you to graph data, that knowledge to quickly ramp up and become a graphista in no time. This is episode 1.
Graph database
We'll
is one type of the NoSQL.
Evolution of databases and explain the problems that graph databases were created to solve. Now, data used to be stored like this: punch tape or punch cards. It's a horrible way to read and understand data. It's impossible to index easily, to cross reference, to eliminate inconsistencies. But it was the best that we had at the time. The industry evolved. We started storing data in tables and relational databases. Sometimes those tables were human readable. But as soon as you normalize the data to eliminate duplication and inconsistencies, many fields start referencing auto-generated numerical foreign keys. And your data becomes difficult to understand and maintain without complicated join queries. But relational databases came with a key feature: ACID support. This meant that you could trust that once the data was committed, it would be accessible to future queries. It's expensive to find data, though. So we add indexes, which make lookups faster. But if we do a bunch of joins, then we have to perform query time index lookups for each and every join. That's fine if we normalized into just a handful of tables. But what if it's 20 tables? Well, that's really expensive. And it gets more and more expensive as your data size grows. Now, over the last 10 years, the cloud came along and things got a bit murkier, a bit less comfortable. Why? Well, there's been a data explosion. Exabytes and exabytes. What do we do with it? We can store it on disk for sure, but how do we make it easy to query? Can our database technologies keep up? Relational databases certainly couldn't handle this volume of data. So innovation took off, and the NoSQL revolution was born. The NoSQL revolution was about making it possible to query more and more data. In order to do this, though, we had to discuss trade-offs. What trade-offs could we make that would make our databases faster? ACID was the first requirement to go. We threw it out the door. After all, with millions and millions of transactions, it's probably okay to lose a couple here and there, right? Developer experience was also critical. How can we make it easier and easier to interact with large volumes of data?
we needed to invent, or at least popularize, different interfaces for our developers. The most simplistic of these is a key value interface. You store a value with a corresponding key. Later, you can use that key to access the value. But the value is opaque. It's meaningless to the database. But what if you don't want opaque values? What if you want the database to index the values and make it easy to query based on the content? Well, that's what a document database is all about. It's a key that looks up a document, but you can also look up a document based on its contents, which are indexed for fast retrieval. Now, what if we care less about the discrete bits of data and more about the relationship between our data? One document can reference another, but this isn't very performant or friendly from a developer perspective. Enter graph databases, a relationship-first approach to storing and querying your data. They store data in a much more logical fashion, a way that represents the real world and prioritizes the representation. But data integrity is important for many developers who care about data relationship. So we brought ACID back to at least one NoSQL database, Neo4j. This allows us to use Neo4j as a transactional data store, storing your most critical business data. Later in this series, we're going to show you how to move your relational database data into a real relational database, a graph database. It's a simple transition that will give you a more intuitive data model, faster queries, and better agility to adapt to changes in the business. Next up, we are going to be talking about graph databases for social fraud detection.
So first type from this NoSQL systems or types key value, as you watched in the video. Key and the value. The value here is not like one shot value. It's like value here. It could be like a combination here, complex value. Complex value means like you have like two pairs, like price and the value, name and its value. So you have complex value for every key.
A key value store is a database that consists of keys. Arbitrary values such as 7000, bytemonk, or 1, 2, 3. As you can see, it is quite similar to a dictionary or a map data structure. Now, in one of my previous videos in system design playlist, we learned the benefits of structure which relational database imposes, because it gives us a very powerful and complex querying capabilities. However, depending upon the use case, the same structure can be more cumbersome than useful. And in those cases, you may prefer to use a non-relational or NoSQL database. That is, a database that does not need any tabular-like structure. Key value store is one of the most popular type of non-relational databases. As its name implies, a key value store is a database that allows you to store mappings from keys, which are typically strings, to arbitrary values. These values are also stored as strings. But some key value stores will also allow you to store integers or arrays as values. Key value stores can be considered as the most primary and the simplest version of all databases. It just has one-way mapping from the key to the value to store data. The lack of any import structure makes them extremely flexible. For example, if you think about caching, it's a perfect candidate for a key value store, because when you implement caching, you are typically storing values somewhere and access them using a hash, a username, or IP address. Basically, you access them using some sort of a key. Conceptually, you are using a key value model. And so, key value stores are typically the databases used for caching. Redis is a popular example to implement caching. Another example that comes to my mind is of dynamic configurations, which I'll cover in another video, but to explain it briefly, sometimes you may have special parameters that different parts of your system may rely on. For example, I might like to store a value in database indicating if my system is up or not. So I can have a parameter like is launched and a Boolean value true or false determining if the system is launched or not. Since you are accessing values directly through the keys, you don't have to search through the database sequentially one by one, going through every entry. You can just access them directly using keys, which makes them extremely fast. And so you will often get low latency and high throughput when using key value store. At the same time, key value stores usually do not have a querying language as in RDMS to retrieve data. They only provide some simple operations such as get, put, and delete. Hence, the data querying or retrieving should be handled manually at the application level. Now, there are a lot of databases out there, and naturally, there are various types of key value stores. For example, DynamoDB, Redis, Zookeeper, and different key value stores may behave differently. Some key value stores, such as DynamoDB, write data to disk, meaning the data will persist even if they crash or go down. Key value stores, such as Redis, might only write data to memory, and if they crash, you will lose the data stored in them. This is a trade-off you make for faster operation, which, depending upon your use case, might be totally acceptable. For example, if you are using a key value store for caching and you lose your data, it might not be unacceptable for your system. All you will miss is a few cache hits, and once your key value store is back up, you will start refilling the cache and those cache hits again. Some key value stores will give you strong consistency. Some will give you eventual consistency. The point is, there are a lot of key value stores out there, and you have to pick the one that's going to be most useful for the use case you're dealing with. Now, there is absolutely no reason to use key value store over RDBMS for a simple, typical business-based application where data management is more important than the performances. But if your application is more performance-driven, you should certainly use a key value store over RDBMS, since the key value stores are capable of providing much higher performances than RDBMS. Also, if your data model is not hierarchical, you should consider using key value stores over RDBMS. As the key value stores are really simple and easy to handle, data can be modeled in a less complicated manner than in a RDBMS, and it will end up having much better performance than RDBMS as well. As both of these databases types have their own strengths and weaknesses, you should be able to choose the most suited one according to your requirement. You can check out my video on CAP theorem to get an idea on
and another type called column store or column database. This is based on column, so its physical storage of the data is column oriented. So in relational database, the records were based on rows, not column. Now we like this type in from NoSQL is called column oriented or column based. So you have this column and you are storing the data in this direction from up down up down up down, like article IDs, and you have the article IDs, price, you have prices, and everything is based on the columns, not based on like one table and so on. Here it's not tabular but column based. And also I added an interesting video here.
Hi, I'm Jared Hillam. A couple of years ago, I was presented to something called the columnar database. It was accompanied by a demo where the presenter queried several billions of rows in less than 3 seconds. I waited patiently for magic fairies to fly out of the server. But soon after, I realized that this solution was simply taking a far more logical approach to acquiring large sums of data. Today, I'm going to share a simple exercise which will help you see the power of using a columnar database for certain tasks. To illustrate this exercise, I'm going to use a good old Excel spreadsheet populated with some baseball statistics. Let's imagine that you are going to play the role of a traditional database. Before I have you play this role, though, you need to know that there's a rule. You have to read the data from left to right, starting from the beginning of each row as you go from row to row, kind of like reading a book. So let's begin. Traditional database, please retrieve for me all of the American League teams. Okay, I've asked for 2 columns of data, leagues and teams. Here goes. As you read the data, notice that you're retrieving the league and team on each pass of every row, and eventually you'll acquire all of the American leagues and their associated teams. Now, servers do this very quickly. However, what if my request has several billions of rows? You can start to see that reading each row just to grab the league and teams column could take a while. And this is where a columnar database comes in handy. We're going to redo the exercise one more time, but instead of giving you traditional database rules, I'm going to give you columnar database rules. This means you're going to read the data from top to bottom, and you're only going to read the columns I ask you to. Okay, columnar database, please retrieve for me all of the American League teams. Let's begin. Notice that this method skips all the data that isn't related to what you're looking for. Once we're done getting that information, we start with the next column, skipping the columns that you don't need. But wait a second. How does the computer know which league to assign each team it's retrieving? The way it does this is that the columnar database assigns a number to each row of data, allowing it to quickly pair up the many columns that it retrieves. You can see how this really comes in handy when you start reading the teams column. All it needs to know is which number the American League values ended at. In this case, row 258, meaning I just need teams from 1 to 258. Now you probably noticed how the columnar database was repeating American over and over. This is actually another advantage of the columnar database. By using the numbering system in the columnar database, algorithms can be used to simplify the retrieval of data. And you'll find that each columnar database system has highly sophisticated methods of gaining further performance measures. Knowing what I know now, I realized that the presentation I sat through a few years ago wasn't reading billions of rows of data. It was just reading a few long columns of data. Columnar databases can be a very straightforward way of addressing the mounds of data corporations have to wade through. Now, they're not a replacement for traditional databases, but certainly a powerful way of doing highly aggregated analysis. Intricity specializes in providing leading-edge solutions for today's complex data problems. I encourage you to visit Intricity's website and talk with one of our specialists, and I commit to you that we'll live up to our slogan of simplifying complexity.
And another type called document-based or document database, or document stored JSON. So we store in document kind of JSON. JSON, it means like it's written like this, between double quotations, you write k value, k value, k value. This is how we write JSON. This is how we store ID equal 1, the price of this product, this value, the name of the product, this ID number 2, price is this value, the name is this, and so on.
Then what
the one type of this the document database, it's a Mango database. It's very popular, and it's also easy to use. You can download and start playing with it.
Welcome to the MongoDB overview. In this introduction, we'll cover everything from its genesis, benefits, and drawbacks to real-life use cases. Please keep in mind that this is the fourth video in a series about them, as well as written articles of why in our MongoDB overview. Let's take a second to learn more about its genesis. MongoDB history starts in October 2007 in a company called Tengen. The founders were looking for a scalable solution capable of dealing with a high volume in their internal project. And at that time, relational databases were not well suited to handle the kind of semi-structured data they needed. As a result, they decided to build their own NoSQL database with scalability and large amounts of unstructured data handling in mind. Almost 2 years later, in February 2009, Mongo was released as an open source project, and since then, it quickly gained popularity among developers and businesses who are looking for more flexible solutions, of course, compared to relational databases. In 2013, Tengen changed its name to MongoDB, reflecting the growing popularity of the database. And today, Mongo is widely used by organizations of all sizes across various industries. Not to mention, we can choose not only between the community and enterprise editions, but also a cloud-based database as a service called MongoDB Atlas. When it comes to how MongoDB works, it is written in C++ and uses a binary form of JSON to store the data called BSON, which translates to binary JSON. These documents can have fields that hold values of different types, such as strings, numbers, arrays, and even nested documents. Just like rows in relational databases are combined together in tables, Mongo documents are grouped in collections. Of course, with one important difference. Each document can have a different structure. When it comes to scalability, MongoDB uses a sharding architecture to scale horizontally. Sharding, in simple words, allows Mongo cluster to store more data than it can fit on a single server by automatically partitioning the data across multiple machines. In such a situation, each shard contains a subset of the data, and the query will be directed to the appropriate shard based on the query. Of course, MongoDB also provides additional advanced features like complex query language, indexing, full text search, and a replica set mechanism. So, with all of that being covered, we can take a while to learn a couple of MongoDB advantages. Firstly, flexibility. As I already mentioned in this MongoDB overview, documents within a collection do not need to have the same structure or fields, unlike traditional relational databases. Mongo simply allows for a flexible schema and can be a great choice for some projects. Moreover, document-oriented storage makes it relatively easy to work with MongoDB using popular programming languages that have built-in support for JSON. Thirdly, great performance. Mongo is designed for high performance and can handle large amounts of data. Additionally, scalability and high availability. MongoDB can be easily scaled and comes with built-in support for automatic failover and replication. And finally, it's easy to use. Mongo provides a simple command line interface, and it is easily integrated with a lot of programming languages and tools. Of course, I must point a couple of disadvantages in this MongoDB introduction as well. So, firstly, Mongo uses a MongoDB query language, also known as MQL. And although it has the same syntax as document, which makes it really intuitive, it's nothing universal, and we have to learn it in order to work with the database. This is not the case, for example, when working with SQL, of course. Moreover, MongoDB does not support joins, which we know from relational databases. And although combining documents or collections together is still doable, it might be a bit tricky task. Additionally, documents cannot exceed 16 megabytes. And lastly, data redundancy. Due to the lack of joins, we oftentimes duplicate data across the documents, which may lead to harder maintenance. With all of that said, let's figure out when Mongo can be a good choice. So, as the first one, content management. It can be used to store and manage large amounts of structured and unstructured content, thanks to its flexibility. Secondly, the Internet of Things. MongoDB is a popular choice for storing and processing large amounts of data generated by IoT devices. Mongo is not only great at dealing with large amounts of data, but also can handle semi-structured and unstructured data sent by IoT devices. Additionally, e-commerce and recommendation systems. A flexible schema allows for easy storage of various types of product data like prices, descriptions, etc. Moreover, MongoDB support for complex queries and aggregations can help easily create search engines and recommendation systems. And as the last one, a bit more general, real-time applications. MongoDB's low latency and high performance make it a great choice for any real-time application, like social media, for instance. So as the last thing, let's see which companies use MongoDB in their technology stack. eBay uses Mongo to store information on items for sale and to power the search functionality. Additionally, Mongo is used to store data about users' browsing and buying history, which is then used for personalization purposes. Another great example is Vodafone, which uses it for IoT, new 5G innovations, and cloud-native applications. Moreover, Uber makes use of Mongo to store and manage data related to its operations, such as information on drivers, riders, and rides. Of course, the list is much longer and contains over 35,000 customers like Forbes, MetLife, Elementor, and Fiverr. And that's all for this MongoDB overview. I hope that you enjoyed this introduction channel.
So graph database, it's also another type. It's based on now it's also based on, like, you have as you see here, you have the way to distribute your data based on a graph, like kind of you have supplier number and the name, for instance, here, and then you make the data as like article number 1 and the data which belonging to this article number 2 and the data belonging to this. So it's like has nodes, it's kind of nodes with properties, and the like every edge with some properties. I also added here one video to make it more clear for you.
Hi, I'm Jared Hill. Have you ever seen one of those movies where they zoom away from a detective board showing all the pictures, news articles, and notes connected by thumbtacks and yarn? Immediately, you can see the power of connecting the dots in all of those relationships. Imagine taking that detective board and applying a mathematical engine that can query its data relationships. Well, that is a graph database. I want to explain graph databases by starting with the familiar territory of a relational database. One of the main traits of a relational database is the constraining nature of its relationships, and that makes it ideal for processing transactions and building what I would call deterministic analytics. However, these strict constraints often make it too complex to answer questions about distant relationships. For example, imagine you had all the university professor and student data ever gathered. Then imagine you wanted to know the relationship between a group of 10 students originating from completely different universities. Well, at first glance, you'd think since the students didn't go to the same universities, you really don't have a connection. But if we look at their professors, who all attended universities themselves, we can discover that they all shared a common professor when they were students. So now let's zoom in and describe some of the traits of a graph database. First, you have nodes, which are essentially records. Connected to these nodes is a type of relationship which can have a direction and a property associated to it. So in our case, the direction points from the original professor. The relationship type is student underscore of, and the property is the year and semester where they were taught. Now, querying this database isn't like your typical SQL query. The graph database vendors often have their own query language, so that is something the industry is still working out. And that brings us to some of the drawbacks of graph databases. One fairly obvious drawback is the tendency to get a little conspiratorial. Just as at times the detective board on the movie screen can make somebody look crazy, graph databases can infer connections that really don't actually mean anything. For example, imagine the inference you could make if all the students in a previous example ended up dropping out of school. Does that mean that the original professor had some kind of meaningful impact on that bad outcome? Well, look, anything is possible. But we have to be a little more skeptical of such conspiratorial patterns. So graph databases are usually a mechanism for starting questions but not necessarily answering them. Another issue is that it's not uncommon to send a graph database query into an oblivion, often because the query plan can be very difficult to conceptualize. This can lead to incorrect interpretations and slow-running queries. That isn't to say that graph databases aren't fast. In fact, for the types of flexibility they offer, they are often the fastest method realistically available. But that speed is tuned to data attributes and not transactions, which still remain the realm of relational data warehouses. So what we see is data science communities using graph databases to test inferences. The discovery of these relationships and their relevance to the organization often is what gets bubbled up into the data warehouse, thus closing the loop between the openness of data scientists and orderliness of data integration, like I discussed in one of my earlier videos. So graph databases are a component in a larger landscape of data management tooling. I've written a white paper about graph databases titled The Data Detective Board, which you can find in the video description. Additionally, if you're considering graph databases in your architecture, you can reach out to Intricity to talk with a specialist.
So now the target of this lecture to understand that there are other databases, the non-relational databases, and what types of databases available to use there. So the study, so the review of the study goes today to explain the meaning of NoSQL, discuss the difference between constraints of relation and non-relational data models, explain the differences among different available not non-relational systems. So the tasks today, it's this like to convert the following part of job offer letter into JSON document. So this is the task, and you can just go through it. Why not only SQL database? Sorry, I have to share. I hope you can see my screen again. Do you see my screen?
Yes, yes.
Okay, so let's go one by why not NoSQL database are considered more flexible than relational database. Think about the solution here is flexible, more flexible.
I,
Which one? What's your choice? A, B, C, D.
I think A.
A, yeah, because it's schemaless.
Yes.
What does eventual consistency mean with the base constraints?
In this case, I think B.
Yeah, it's B. The data will reach a consistent state eventually. So if you search for a value or you search for a data, as we talked in the videos, you can find the data directly because you don't need to like do joins and selection a SQL statement to reach the things. As to do reach the data, it's like you can reach the right away the consistent state.
Yeah, that was my question. But while you were showing that
Yeah,
picture, but you skip it. Well, my question about this eventual consistency, what is the meaning of this, and what is the atomicity?
atomicity we already studied in like in our first lesson and the third lesson. Atomicity we talked about like the atomic values, if you remember. Do you remember that?
You cannot divide it. That means that?
Yes.
Okay.
But regarding constant state eventually in not only SQL, this is like eBay. So if you click on like some products and the eBay wanted to store, like you clicked on some products, so they can find out like what things you are interested in, like what products you are interested to buy. So I can reach this consistent state eventually. Eventually it means like in real time. Okay. So this eventually consistency for not NoSQL helping like to solve some problems like this in real time, to help you also to find the data faster if you have complex data. Which of the following is an example of document stores? Which one?
Mongo.
It's Mongo database. Yeah, Mongo database. So I advise you to download Mongo database
Mhm.
and work with it. You'll find it a lot of tutorials online to start with Mongo database. It will help you to understand better non-relational databases. So this was the last lecture for this course. I hope you start on your own to train yourself with some practical stuff. You need really to do more practical to understand the relational and the non-relational. In this case, you will train yourself how to adapt with the requirements with different examples and so on. So thanks a lot.
What
Thank
could be your practical advice about like when is non-relational is preferable or when is relational is preferable?
As you watched in the video, if you take more about organizing data, so you need to or data management, you need to use the relational database. So it's easy because you have organization, you have schema, you have relation between the tables, so it's easier to manage. Like if you have a company with like 100 employees and you need to register their, like the time when they come and the time when you go, this kind of database, you don't need huge or big data. So it's for you can build your system based on relational database. It's like employees and their I mean the time, arrival time, the clock in clock out, and you have like kind of reports when they come, when they go. It's like simple. So your database is simple, it's manageable. So in that case, use directly the relational database. What if your data is coming, like you have data about like temperature, about you have a machines in your factory, and in that factory they getting like many data from sensors installed in these machines. So data about temperature, about pressure, about different values from every machine. So and you receive data like every 9 seconds or 10 seconds from these machines or devices. So could you imagine, Turlak, to use a relational database to adapt or work with something like this? Like you have complex data coming from different categories, different values from sensors, from devices, and you need to store this data to cloud. Would you think of using a relational database to handle this?
So in that case, non-relational is more preferable, huh?
Exactly. Run relational database would solve like this kind of like problems, and also kind of if you have a big website like eBay or Amazon. Amazon can get like 1 million order per minute or something. I'm talking about Amazon Globe, like everywhere in every country, and this kind of transactions, this kind of reactions, and also user behavior, and if the user interested in this product, and also they store if you open the product, watched it like multiple times, but you didn't buy it. So they start to analyze why you didn't buy it. And this kind of information you can't get from a relational database. Why?
Hmm.
Because it's based on some tables and the relation between these tables, and it's really consistent based on this data, based on this relation. If you wanted to work like behind that, or beyond that, beyond that, you need to like get the data in real time, and this kind of data like Mongo database would be like a good solution to handle this.
Mhm, mhm.
Okay.
So I
And
hope it, yeah, yeah,
this
go ahead.
transfers, does this transfer, today is the last lecture and this transfer test, the last one.
I
How
mean,
will
if you can just send it per email.
okay.
So I mean, I hope you will succeed with your exams. And database and database modeling, it's very important topic, very very important, and you need it in your technology path anyway. And if you really need to understand these topics, it's not about lectures, it's about you. It's about you. You need to try many things. You need to try these things practically, to build everything from scratch practically. And when you build things, you will meet many issues, and you will meet many problems to write code. Sometimes it doesn't work, and then you search more and more. And when you search, you will find many solutions, many suggestions. In that way you can learn. So I
Mhm.
hope you can find your way with this practical stuff. And if you need any help, you can always write me per email.
That's great.
Thanks a lot. Thanks for your
Well,
time.
thanks a lot for the
Thank
nice
you.
and amazing lectures. And yes, hope to meet you again.
The same here. Thanks a lot. Thank you. Have a nice
Thank
evening.
you.
Thank you. Bye
Bye
bye.
bye. Bye
Bye
bye.
Bye bye.
bye.